Hello, welcome to video 14 in the lecture Advanced Mathematic Modeling. In the last videos I showed you how to transform random variables, and we had an application where we used this to be able to generate exponentially distributed random numbers in the computer. And then I promised you to give you another application of this transform. But before we do this, I thought it might be better to introduce at this point now power law distributed random numbers, so that we can contrast this a little bit to exponential random numbers, because like this difference between these two functions will be a kind of central theme, a red line to the rest of this lecture, and we want to understand better what does it mean if random numbers are distributed by a power law. And maybe it's a good idea to start when we learn to generate random numbers, that we directly learn how to generate power law distributed random numbers, because we will need this so often. So first let's look at the difference between these two functions. And in particular it will be the difference between an exponential function. In general we can write this a to minus x versus a function, a power law, x to minus alpha. And so what's the difference between these two types of functions of x? So first let's look at the exponential. So if we have a function, and now we don't speak for a second not about distributions, it's just also for functions. So let's say we have an exponentially decaying function. So that's exponential. And you all know an exponential function is a function which has at 0 has a certain value and then is decaying, and then has small value for large x. And this function is kind of the epitome of a function which is decaying very rapidly. So after some time this function just disappeared. So what's a power law function? And with the first glance such a function looks very similar. First exponential, so we write it as e to minus lambda x, and this always can be also written as a to minus some lambda x. So now we want to contrast this to power law function, x to power minus alpha. And I mean, this looks so similar, it's just you invert what's here and there. And the power law is also a decaying function. Decaying function of x. So, but there are some crucial important difference, even though at first glance you might say these functions look very similar. So the first obvious difference is in the behavior at x equal y. So this function diverges, and for x equals 0 it's infinite. And if later we would like to have a power law as a distribution, so the area under the function must be finite, normalized, so we need a smallest value. We need to decide for some x0, and here we say this function is only defined for x larger than this x0. Whereas here we have a function which is defined for x larger than 0. I mean, in principle, of course, you can extend the exponential also negative values. Yeah, that's of course possible. In the power law, in principle, you can have of course minus x to some power. But if we later go to distributions, for exponential distribution, we have a variable which is larger than 0. But for a power law distributed random number, we have such cut-off value. And this needs to be defined. So actually the power law distribution has a second parameter, the cutoff. Very often the cutoff can be 1 if you scale. So we can scale the variable so that the cutoff is 1, but it doesn't really matter, but we need the cutoff, otherwise the power law would diverge. So that's the first difference. So exponential and power law differ for very small values, but they differ also for very large values, even though it's maybe not so obvious here. And the thing is, the exponential decays much faster than the power law. And how can we see this? We can see this if we make a double logarithmic plot. And that's very often, it's very important often when we have power law distributed values. So we plot here log x, and here we plot, if this is the y, we plot here log y. And then the power law, if you transform, so if we make this double logarithmic plot, then the power law will be a straight line in this plot. Why? Because if we have here y equals x to minus alpha, if we now make a log of this, then log y, we have a constant here, equals log y equals log of our constant minus alpha log of x. So in the log variable, this is just a linear function. Also note that if you make log x's, now the x's go from minus infinity to plus infinity. I mean, here we go, of course, we stop somewhere at log of x0, but that's not necessarily for positive values. So in log x's, we can always typically go to the negative. And here, so we have a straight line with slope minus alpha. And so this means even though the function is decaying, for every large value of x, you know, if you have a logarithmic value, so this, if you go to the right here, this corresponds to very huge values in the unlocked variables. We have some contribution. Now, if we make a double logarithmic plot of an exponential, log x, log y, this will look more something like this. So it's a function which for small values has smaller slope, and for large values suddenly drops tremendously. So this means the exponential function is really dropping at a certain characteristic scale given by 1 over lambda. Yeah. So that's the maximal possible values that are allowed, and larger values don't appear, whereas in the power law, values appear in all scales. Yeah. So there have some similarities when you look at them, but the functions are inherently, fundamentally different. And in one of the homeworks, I give you, maybe you would say, tedious exercise to plot these two functions for all parameters and all x values. But that's so important that when you see an exponential value and you have a certain exponent here, that you directly know how to plot it and what are the properties. Okay, anyhow, so like that's now, we now look at the power law, now we take a distribution, and now we want to know how can we calculate these in the computer. So let's assume we have a power law distributed random number, y, and we have our density q of y, and when you compare what we did later in some previous videos with the exponential distribution. So you saw also there we used the notation y and q of y, so to use our formula so that's why I also now use the notation of y. So we have our exponent and our cutoff value y0, and first we need to look for this normalization. So what is the normalization? And so how we normalize this? So we want that 1 equals the constant, the integral from y0 to infinity y to minus alpha dy. And then this calculation with power laws always involve these kind of integrals. So y integrated y to minus alpha integrated gives our constant over 1 minus alpha, and then we have here the function y to 1 minus alpha between y0 and infinity, and then we write this as c over 1 minus alpha, and now this function here at infinity goes to 0, and here at this point we have y0 to 1 minus alpha, and so this is c over alpha minus 1. Here I use the minus sign to change this, times y0 to 1 minus alpha, and this should be 1. And from this we obtain the normalization constant. The normalization is alpha minus 1 over y0 to 1 minus alpha. So that's the normalization for power law distribution. But here I made a small assumption. When I assume that this y to 1 minus alpha at infinity, that it really goes to 0, this holds only if this alpha is larger than 1. So this means we can normalize this distribution only if alpha is larger than 1. So this means these power law distributions are defined for exponent alpha larger 1. And for smaller values of alpha, these distributions are not normalizable. So alpha equals 1 would be the marginal case. So now in order, so like we have this, so of course now we can also would be interested to calculate standard deviations, expectation, and so on. This we will do later, because we will have a lot to say about power law distributions. For the moment we will need the cumulative distribution, because we want to calculate, to draw random numbers. So calculate the cumulative distribution. So how to do this? So we calculate this q smaller of y. This is again such an integral from y0 to y, q y bar d y bar. Okay, now we have to plug in our distribution and our normalization. Let's keep the normalization for the moment just c, and so we integrate c y0 until y bar to minus alpha dy bar. Now we integrate this. It's very similar as we did before. And we get c over 1 minus alpha. And then we get y to 1 minus alpha between y0 and y. Maybe we still have a prime. And then maybe now it's a good time to plug in this normalization constant c. We can put this in here. So this 1 minus alpha, this cancels. So we have minus 1. And then now we integrate. Then we have still this y0 to 1 minus alpha. And then we have this term in the two borders. And we have y to 1 minus alpha minus y0 to 1 minus alpha. So you see, it's maybe not the most simple calculation, but typically with these power laws it goes straight forward. You just have to follow through. And now we can see here we have this division over y0. We can put this to both sides, and then here this cancels. So we can write this as 1 minus y over y0 to 1 minus alpha. And this is the cumulative distribution of our power law. And then we see 1 minus something of the cumulative, this q smaller equals the q larger. So we see that the other cumulative distribution, this q larger of x, then is just y minus over y0 to 1 minus alpha. So it's an interesting side result that this cumulative distribution of a power law is again a power law. Here's a different exponent with the exponent. Minus alpha. So now we have this, and what were we actually interested? We wanted to generate random numbers from the power law distribution, and now we have to remember our trick. So we assume our computer produces uniformly distributed random number, and then we have calculated the cumulative distribution, and then we say, okay, our uniformly random number equals just the cumulative distribution. That was our formula. So what we do now, in order to generate the random numbers, we say our x equals the cumulative distribution. This is this here, 1 minus y over y0 to 1 minus alpha. And now it's very similar to the case in the exponential distribution. We solve this for y, and then y equals y0 times 1 minus x over 1 over 1 minus alpha. And this is already the formula how you can generate this power laws. But then we remember that if x is uniformly distributed in between 0 and 1, then 1 minus x is also uniformly distributed. So we just can take the more simple formula that y equals our cutoff y0 times this uniformly distributed random number x prime to power 1 over 1 minus alpha. And so here we have the simple formula. If we take a random number generator which gives us uniformly distributed random numbers, how we obtain power law distributed random numbers. And when you compare this in the case of the exponential distribution, maybe I make this also red here. So this is quite similar formulas. In the exponential distribution we take this x prime and then multiply, take the logarithm, and here we take this x prime and take an inverse power. So now we have we know how to have some first insights into the algebra of power law distributions. We know how to normalize them, we know the cumulative distribution, we know how to generalize them, and we have some first idea how they look like, and we see some deviations from the exponential distribution. And this interesting fact is that they are so linearly on a log-log scale, and this will be very important later. For the moment, thank you.